Welcome to our video on the half-value layer, or HVL, a crucial concept in radiation protection. This content is for anyone interested in understanding how we minimize exposure to radiation, from students of health physics to professionals in nuclear medicine and industrial radiography. By the end of this video, you'll have a clear grasp of what HVL is, why it's important, and how it's applied in real-world scenarios, ultimately enhancing your knowledge of radiation safety. Radiation shielding is fundamental to safety in environments where ionizing radiation is present. It's about creating barriers that reduce the intensity of radiation to safe levels. This protection is vital in various fields, including healthcare, nuclear power, and research, where controlling radiation exposure is paramount. But why is shielding so necessary? Ionizing radiation carries enough energy to remove electrons from atoms, potentially causing damage to living tissue and even DNA. Prolonged or excessive exposure can lead to serious health effects, from acute radiation sickness to increased cancer risk. Shielding is our primary defense. Before we dive into HVL, let's briefly touch on different types of radiation. We primarily deal with alpha, beta, gamma, and X-ray radiation. Each type has different penetrating powers, requiring different shielding approaches. Alpha particles are easily stopped, while gamma rays and X-rays are highly penetrating and require more robust shielding. Now let's define the star of our show, the half-value layer. The HVL is a critical concept for understanding how effectively a material reduces radiation intensity. It gives us a standardized way to measure shielding effectiveness, regardless of the radiation source or material. So what exactly is the half-value layer? Simply put, the HVL is the thickness of a specific material required to reduce the intensity of an X-ray or gamma ray beam by half. Imagine you have a certain amount of radiation. The HVL tells you how much material you need to cut that amount in half. The HVL is measured by incrementally increasing the thickness of a shielding material and monitoring the radiation intensity. We continue adding layers until the initial intensity is reduced by 50%. This measured thickness is the HVL for that specific material and radiation energy. Let's see how HVL works in practice. If you have a radiation source with an intensity of 100 units, and the HVL of lead for this radiation is 5 millimeters, then 5 millimeters of lead will reduce the intensity to 50 units. Another 5 millimeters will reduce it to 25 units, and so on. Each HVL reduces the intensity by half. This concept of exponential reduction is key. It means that while the first HVL reduces the intensity by half, subsequent HVLs continue to reduce the remaining intensity by half. This is why thicker shields provide increasingly significant protection, though there are diminishing returns after a certain point. The HVL is directly related to the density and atomic number of the shielding material. Denser materials with higher atomic numbers, like lead, typically have smaller HVLs because they are more effective at absorbing or scattering radiation. This means you need less of a dense material to achieve the same reduction. The applications of HVL are widespread. In medical imaging, HVL is used to ensure proper beam quality for X-ray machines, optimizing image quality while minimizing patient dose. In nuclear power plants, it helps design containment structures. For radiation workers, HVL guides the selection of personal protective equipment. Understanding HVL is crucial for designing effective radiation protection barriers. Engineers and health physicists use HVL values to calculate the necessary thickness of walls, doors, and other shielding components in hospitals, laboratories, and industrial facilities, ensuring safety for both workers and the public. Common materials used for shielding include lead-hour, which is highly effective due to its high density and atomic number, and concrete, a more economical choice for large-scale shielding. Other materials like steel and water are also used, depending on the type and energy of the radiation. The importance of HVL in safety cannot be overstated. It provides a quantitative measure for assessing radiation hazards and designing appropriate countermeasures. Without HVL, it would be much harder to reliably ensure that radiation levels are kept within safe limits. Ultimately, HVL helps us achieve the ALARA principle, as low as reasonably achievable. By precisely calculating the shielding needed, we can effectively limit radiation exposure for both occupational workers and the general public, protecting them from harmful effects. Ensuring occupational and public safety is the core mission of radiation protection, and HVL is a fundamental tool in achieving that. It allows us to build a safer world where the benefits of radiation technology can be harnessed responsibly. In conclusion, the half-value layer is a powerful concept in radiation protection. It provides a standardized and practical way to quantify the effectiveness of shielding materials, ensuring safety in diverse applications. From designing medical facilities to ensuring the safety of nuclear operations, HVL plays a pivotal role. It is a testament to how scientific understanding can be translated into practical solutions for safeguarding health. Remember, HVL is the thickness of material needed to reduce radiation intensity by half. It depends on the material's density and the radiation's energy. Its application is vital for safely managing radiation exposure. Feel free to reach out if you need further information. Nuvia is your lifecycle partner for highly regulated environments. We work to build a safer, cleaner, and more sustainable world.